Welcome. Today we're going to start our first linear algebra tutorial. So let's begin with our first question. So in the first one it says let u equal 5, 3, minus 4. Now these are vectors incidentally, and w is 3, minus 1, 2. Okay, so find 5u minus 2v in part A. So this is a linear combination of u and v. We have a sum of scalar multiples of u and v. And so let's set this up. This is 5 times the vector 5, 3, minus 4, minus 2 times the vector minus 1, 5, 2. We multiply those scalars in, and then we add the result. So we have 25, 15, minus 20, plus 2, minus 10, minus 4. And so this gives us 25 plus 2 is 27, 15 minus 10 is 5, minus 20 minus 4 is minus 24. Okay, and so we're done with part A there. Now let's move on to part B. Calculate minus 2u plus 4v minus 3w. So similar here. So we have minus 2u plus 4v minus 3w. Okay, so we multiply those scalars in and then we add the result. Minus 10, minus 6, 8, plus minus 4, 28, plus minus 9, 3, minus 6. Okay, so now we add these numbers row by row. We have minus 14 minus another 9 is minus 23. 23 minus 6 is 17. Then we have 16 minus 6 is 10. Okay, so now I'll show you how to do this in Mathematica just to be fast about it and accurate. So when I enter this, I'm going to put brackets around every one of these entries. And so that's the way to write this as a column vector. Okay, so now that I have the 3 of these vectors entered into memory, or not entered in because I haven't pressed the button yet, but I'll soon press the button. I've just typed them up. Okay, so now I'll just write 5u minus 2v, shift and enter, and so there we have it. But what I can do now is display this as in this form, just like that. So 27, 5 minus 24. All right, so now let's do part B this way. Okay, let's press this. Minus 23, 17, and 10. So just like we got here, doing that by hand. Okay, so let's move on now to question 2. So question 2 says write the vector, and now I'm going to write these as a column. You can see that they're written in forms as a row just because it saves vertical space on the page there when I type it up, but I'm going to write it as a column. So 1 minus 2, 5. Write this as a linear combination of the vectors u1, 1, 1, 1, u2, 1, 2, 3, and u3, 2, minus 1, 1. Okay, so what this means is we have to find scalars, say alpha, beta, gamma, and so these are real numbers, and so that's what I'm writing here. They're elements of the set of real numbers, such that alpha u1 plus beta u2 plus gamma u3 is equal to v. And so to do this, well, you can guess, but that can come up unsuccessful. So what you want to do is set this up, and then you're going to solve a system of equations for alpha, beta, gamma. So let's write alpha times u1, beta times u2, gamma times u3 is v. Okay, and so now if we expand, multiplying those scalars in and add the result, then we'll see that we have a system of 3 scalar equations that we can get from one vector equation right here. So let's do that. So we have alpha times 1 plus beta times 1 plus 2 gamma in the top row. Then we have alpha plus 2 beta minus gamma in the second row. Then we have alpha plus 3 beta plus gamma in the third row. This is equal to the vector 1 minus 2, 5. Okay, so one vector equation that gives rise to 3 scalar equations. And so those are the equations. Alpha plus beta plus 2 gamma is 1, and so on. So here we have our 3 scalar equations. All right, so now what we can do is interpret this as a matrix equation. And so I'll read off the coefficients there on the left, and here's a corresponding matrix equation. Okay, so notice what this is. So the matrix on the left-hand side is the concatenation of U1, U2, U3, and the matrix on the right is V. So let's just note matrix A on left is U1 concatenated with U2 concatenated with U3. Okay, so how do we solve this matrix equation? Well, we can do Gaussian elimination to find alpha, beta, gamma. We can go into Mathematica and we can ask to solve this system right here. So we'll do this in a couple of ways. So let's do this by Gaussian elimination. So the augmented matrix, so we have A concatenated with V, this one right here, which is this 3x4 matrix. Okay, and now what we want to do is row reduce this, seeking out the row reduced echelon form of this matrix so that we can find alpha, beta, and gamma. Okay, so let's perform row operations on this matrix here. And so when I have performed a row operation, I will use a tilde beneath rather than an equal sign. Okay, and now my goal is to get zeros under my leading pivot, to get zeros above and below my second pivot, and to get zeros above my third pivot. All right, now I do this in a somewhat different way than some people do. In this variation of the Gauss-Jordan algorithm, what I do instead of get ones in my pivots, I will just seek an integer, a positive integer in my pivots. And if that's not 1, then I don't care. At the end, I divide throughout by the numbers on those pivots so that I get the number 1 at the end and only at the end. And the reason why I do that is so that I can avoid fractions for as long as possible, because as a human, it can be a little bit tricky to add, subtract, and multiply with fractions accurately, right? We often make mistakes when we do that. So I try to avoid it until the last moment. Okay, so that's what we'll do. Now, I have a pivot here. I'm okay with that. It happens to be the number 1. So I want zeros below that. So I'm going to just copy down the top row. Okay, and now the second row, let's let that be row 2 minus row 1. So we have 1 minus 1 is 0, 2 minus 1 is 1, minus 1 minus 2 is minus 3, minus 2 minus 1 is minus 3, and so this was row 2 minus row 1. Okay, next, let's do the same thing with row 3. Row 3 becomes row 3 minus row 1, and the reason why I want to do that is because I get a 0 here, but also it retains a positive number here. So 1 minus 1 is 0, 3 minus 1 is 2, 1 minus 2 is minus 1, 5 minus 1 is 4. Okay, so now we've achieved our first goal, which is to have zeros beneath our first pivot there. Next, we want to have 0 above our second pivot and 0 below our second pivot. So here is our second pivot. So then let's replace row 1 with row 1 minus row 2. Okay, so we have 1, 0, 2 minus minus 3 is 5, 1 minus minus 3 is 4. Okay, I will keep row 2 the same. And now, hang on, I can see that I'm going to want to subtract with this 2 in row 3. So instead of keeping row 2 the same, I will multiply it up by 2. So let's write that row 2 goes to 2 row 2. And so let's actually do that now. 2 will be minus 6 and minus 6. Okay, for now I will just copy down row 3 the same. Okay, so let's go to our next step, which is to have a 0 where this bottom 2 is. Okay, so we keep row 1 the same. Row 2 becomes the same. So we want a 0 where this bottom 2 is. Okay, so row 3 becomes row 3 minus row 2. Okay, so 0, 0, minus 1 minus minus 6 is 5. 4 minus minus 6 is 10. Okay, there we go. So I'll grab a new page. Okay, so on this new page, what I want to do is divide throughout by the GCD in row 2 and in row 3. So GCD of 5 and 10 is 5. So I'm dividing that row by 5. And so this is what we have. Okay, so now we have a 1 in our first 2 pivots. Now I want to have zeros above my last pivot where the 5 and the minus 3 are. So I want everything in this column to be, well, let's make it all in terms of 15. So I'll multiply row 1 by 3, multiply row 2 by 5, and multiply row 3 by 15. Okay, and so now let's replace row 1 with row 1 minus row 3. Let's replace row 2 with the sum of row 2 and row 3. And then let's divide row 3 by 15. And so we're almost done. We just need to make these pivots be 1. So let's divide the first row by 3, the second row by 5, and keep the third row the same. Okay, and so this gives alpha equal to -6, beta equal to 3, and gamma equal to 2. So now let's go to Mathematica and do the same thing there. Okay, so I have, using the palettes, typed out the 3 equations, used a double equal sign there because I'm not putting this in memory. Okay, so now I'm just going to write solve, and we get alpha, beta, gamma is -6, 3, and 2, just like we got on paper here. So that's one way to do it. Now, another way to do it would be to insert this augmented matrix. So alternatively, now I will go to insert table matrix new, 3 rows, 4 columns. Okay, and then I'll just enter this matrix here. Okay, so the matrix is entered there. Now what I'll do is I'll just write row reduce and then ask to display this as a matrix. Okay, so there we have the row reduced echelon form of that matrix, and the right hand column tells us that alpha is -6, beta is 3, and gamma is 2. Question 3 asks us to find the dot product or scalar product, where in part A, u is the vector 2 minus 5, 6, v is the vector 8, 2, minus 3. Okay, so the dot product is the sum of the product of each corresponding entry, so u dot v. And it makes more sense to do this with these written vertically because then you can visually line them up, components that is. Okay, and so we have 2 times 8 plus -5 times 2 plus 6 times -3. So that's 16 minus 10 minus 18, which is -12. Okay, now part B. So here we've got u equal to the vector 4, 2, minus 3, 5, minus 1. V is the vector 2, 6, minus 1, minus 4, and 8. So u dot v is, so we multiply these across and add the result. So that's 8 plus 12 plus 3 minus 20 minus 8. And so 23 minus 20 is 3. 3 minus 8 is -5. Okay, question 4. U is the vector 5, 4, 1. Now, incidentally, I should say here that me writing this as a column, that's not exactly the same vector as what is written there. Okay, so this is abuse of the notation, me just thinking of this as the same. What you want to do is write it down one way and then be consistent. This is U. Then I'll write V as 3 minus 4, 1, and W, 1 minus 2, 3. Okay, so which pair, if any, are orthogonal? So this is the question, which pair has a dot product equal to 0? So we'll calculate U dot V. So we have 15 minus 16 plus 1. And so this is 0, so U and V are orthogonal. Okay, so now let's take U dot W, 5 minus 8 plus 3. Okay, so this also adds up to 0. So U and W are also orthogonal. So now let's take V dot W. So 3 plus 8 plus 3. So this is 14. That's not 0. So V and W are not orthogonal. Question 5. Find K such that U and V are orthogonal. So in part A, we have U equal to the vector 1k minus 3. V is 2 minus 5, 4. We've got to find K such that the dot product of U and V is 0. So U dot V is 2 minus 5k minus 12. And so we're seeking K such that this is 0. Simplifying this, we have 2 minus 12 is minus 10. Let's take that minus 10 over to the right-hand side. So minus 5k equals plus 10. So k is equal to 10 divided by minus 5, which is minus 2. Part B, U is 2, 3k minus 4, 1, 5. And V is 6 minus 1, 3, 7, and 2k. Okay, again, let's take the dot product of these two vectors. So this is what we get. Now we need to simplify this. 12 minus 12 is 0. So we have 7. 10k minus 3k is 7k. Okay, so 7 plus 7k is 0. So solving this for k, let's take that 7 over to the right-hand side. We have 7k is minus 7. So dividing throughout by 7, k is minus 1. So if k is equal to minus 1, then the vectors u and v are orthogonal. Question 6. Find the norm of u, where u is the vector. I'll just write it as a row this time. Okay, so the norm of u is the square root of the sum of the squares of the entries. And so we have the square root of 9 plus 144 plus 16. Okay, 144 plus 16 is 160. So we have 169 inside the square root. And so isn't that 13 squared, 169? So yes, this square root is 13. Okay, part B. So this time u is the vector 2 minus 3, 8 minus 7. And so the norm of u is the square root of 2 squared is 4, minus 3 squared is 9, 8 squared is 64, minus 7 squared is 49. So 113 plus 13 is 126. So we have the square root of 126. Okay, question 7. So u, v, and w, they're vectors in 2, 3, or 4 space. And so we're asked to calculate unit vectors u hat, v hat, and w hat. Okay, so let's begin with u hat. So u hat is 1 on the norm of u times the vector u. Now, the norm of u is 5 because the square root of 3 squared plus 4 squared is the square root of 25, which is 5. So we have 1/5 of the vector 3 minus 4. Now, if you want to, you can take that 1/5 in. I tend to like to leave the fractions out the front. Okay, so v hat is 1 on the norm of v times the vector v. So calculating the norm of the vector v there, we have the square root of 16 plus 4, which is 20, plus another 9, so 29. 29 plus 64, 93. So 1 on the square root of 93. Okay, now w hat. So first let's write w by pulling out the common fraction there. So let's write everything here over 12. So 1 on the norm of w, and then I'll just rewrite w as 1/12 of 6, 8 minus 3. Okay, now let's take the norm of this vector. So we have norm square root of 109 divided by 12. So the multiplicative inverse of that is 12 over the square root of 109. Okay, question 8. So in question 8, we have vectors written in terms of ijk, but I prefer to write these as columns. So that's 2 minus 3, 4, and v is 3, 1 minus 2. W is 1, 5, 3. So the first one says calculate the cross product u cross v. So the conventional way to do this is to express this as a determinant. We put I, j, k in the top row. We put u in the second row, v in the third row, and then we calculate this determinant. It's not a real determinant because we have vectors in the top row, and so this is just an aid to memory of the calculation of the cross product. Okay, so calculating this, we have minus 3, 4, 1, minus 2, I hat, minus 2, 4, 3, minus 2, j hat, plus 2, minus 3, 3, 1, k hat. Okay, now calculating each of those 2 by 2 determinants, we have 6 minus 4 is 2, so 2 I hat, and then minus, keep the bracket around this because it's a little bit tricky when you have multiple minus. So that's minus 4 minus 12, j hat, and then plus 2 minus 9, 2 plus 9, so that's 11 k hat. Okay, and now simplifying, this is minus 16 inside the bracket, but we have another minus, so that's plus 16. So then 2, 16, 11, and I'll write that as a column again. And so this is our cross product of u cross v. Okay, now question part B, u cross w. Now we write w in the third row. And so this is minus 3, 4, 5, 3 I hat minus 2, 4, 1, 3 j hat plus 2 minus 3, 1, 5 k hat. Okay, so simplifying this, we have minus 9 minus 20, so minus 29 I hat, and then 6 minus 4 is 2, so minus 2 j hat, 10 minus minus 3, so that's 10 plus 3 is 13 k hat, which we can write as a column minus 29 minus 2, 13. Okay, question 9. Again, calculate some cross product. So U cross V is, we have this, and then we expand this. Okay, simplifying, we have 12 minus 15 is minus 3 I hat, minus 6 minus 12 is minus 6 j hat, plus 5 minus 8 is minus 3 k hat. Okay, so simplifying that, we've got the column minus 3, 6, minus 3. And this is U cross V. Okay, part B. So expanding this in the same way. Plus minus 4, 7, 6, minus 5. Determinant times K hat. Okay, so simplifying this. 7 times 2 is 14. So 14 minus minus 15 is 14 plus 15, 29 I hat. And minus 8 minus 18 J hat plus 20 minus 6 times 7 is 42 K hat. Okay, so minus 8 minus 18 is minus 26, but then we have another minus, so that's plus 26. And then 20 minus 42 is minus 22, so this is U cross V. Question 10. So we have U is the vector 1, 2, minus 2. V is the vector 3, minus 12, 4. K is equal to minus 3. Okay, part A says calculate the norm of U, among other things. So the norm of U is the square root of 1 squared plus 2 squared plus minus 2 squared. And so that is the square root of 1 plus 4 plus 4. The sum is 9, so the square root is 3. So the norm of U is 3. Now the norm of V is the square root of 3 squared plus minus 12 squared plus 4 squared. So we have the square root of 9 plus 144 plus 16. So that's the square root of 169, which is 13. Okay, now let's take the norm of the sum of U and V. So first we need to add U and V. So we have the vector 4 minus 10 minus 2. No, plus 2. Okay, so taking the norm of this, 16 plus 100 plus 4. So that is the square root of 120, which we can simplify a little bit here. This is 12 times 10, or 4 times 3 times 10, 4 times 30. So we can write 2 root 30. Okay, next, calculate the norm of K times U. So this is the norm of minus 3 times the vector 1, 2, minus 2. And so let's multiply it in first. And so we have the square root of 9 plus 36 plus 36, which is the square root of 81. And so that's 9. So incidentally, in general, the norm of K times a vector U is the absolute value of K times the norm of U in general. Okay. All right. So in part B, the first part of that asks us to do this. All right. So why don't we do this more generally than just with those vectors? So now let's let the vector U be U1, U2, U3, etc. to UN. Okay. And so then the norm of K times U for some generic scalar K is the norm of the vector K, U1, K, U2, etc. up to K, UN. Okay, now taking the norm of this, we have the square root of K, U1 squared plus K, U2 squared, and so on, up to K, UN squared, square root. So expanding this, factorizing gives K squared U1 squared K squared U2 squared, and so on, but there's a common K squared, so we can write K squared outside of U1 squared plus U2 squared, and so on, up to UN squared. Now the square root of K squared is the absolute value of K, and so then what we have left over is the norm of U. which is the result in general. Okay, so now the next one is the triangle inequality. So let's verify this with the numbers. Okay, so we have already calculated that the norm of the sum is 2 root 30, and the sum of the norms is 3 plus 13, which is 16. So is 16 greater than 2 root 30? Well, yes, because 36 is greater than 30, and the square root of 36 is 6. 2 times 6 is 12. So yes, 2 root 30 is strictly less than 16. Okay, question 11. Find k such that u and v are orthogonal. So in part A, we have 3k minus 2 dot 6 minus 4 minus 3 is equal to 18 minus 4k plus 6, which we suppose is equal to 0. And so that is 24 minus 4k equals 0. Take the 4k over to the right-hand side and then divide by 4. And so we get k is equal to 24 over 4, which is 6. All right, now part B, u dot v is 5k minus 4, 2 dot 1 minus 3, 2, 2k. So this gives us 5 minus 3k minus 8 plus 4k equals 0. And so that is k minus 3 equals 0. So k is equal to 3. Okay, part C, u dot v. So we have 3 plus 7k minus 3k minus 6 minus 2k equals 0. So that's 2k, or 7k minus 3k minus 2k. And then minus 3, which is 3 minus 6, equals 0. And so k is equal to 3 over 2, or 1.5. Okay, question 12. So let's write these vectors as columns. That'll make things easier in my opinion. 3 minus 4, 2. And we have 2, 5 minus 3, 4, 7, 2. So 2u minus 3v is 6 minus 8, 4 plus minus 6 minus 15, 9, which is 0, minus 23, and 13. Part A. Okay, part B, 3u plus 4v minus 2w is 9 minus 12, 6 plus 8, 20 minus 12 plus minus 8 minus 14 minus 4, which gives us 9 minus 6 minus 10. Okay, part C. So u dot v, just looking at these, we have 6 minus 20 minus 6, which is minus 20. U dot w, looking at these, we have 12 minus 28 plus 4. So 16 minus 28, so minus 12. Okay, v dot w, again, looking at these, so that's 8 plus 35 minus 6, so which is 2 plus 35, and so that's 37. Okay, part D, taking the norms of these vectors. So the norm of u is the square root of 9 plus 16 plus 4, so the square root of 29. The norm of v is the square root of 4 plus 25 plus 9, which is the square root of 38. And then the norm of w is the square root of 16 plus 49 plus 4, which is the square root of 69. Question 13. So we have u equal to 3 minus 4, 2, v equal to 2, 5 minus 3, w equal to 4, 7, 2. And we are asked to calculate cross products. Okay, so u cross v is this. Okay, so simplifying this, we have 12 minus 10 I hat minus 9 minus 4 j hat plus 15 plus 8 k hat. So that's minus 2 I hat plus 13 j hat plus 23 k hat, which we can write as a column. Part B, u cross w. Okay, expanding this, we have this. Okay, simplifying. Now we need to tidy up this and then write this as a column. Okay, part C, v cross w. Expanding the determinant. Okay, simplifying this, 10 minus minus 21 is plus 21. And simplifying the arithmetic gives 31 I hat minus 16j hat minus 6k hat. And so we'll write this as a column, 31 minus 16 minus 6. Question 14. Find a unit vector u hat orthogonal to v and w. So the first thing we would want to do here in part A is take the cross product of v and w. So the cross product gives 7, 1, minus 3. Okay, so now this vector is perpendicular to both v and w, but if we're to find a unit vector u hat perpendicular to v and w, then we need to divide by the norm of. So u hat is 1 on the norm of u times the vector u. And so taking the norm of this, we have square root of 49 plus 1 plus 9. So 1 on root 59, 7, 1 minus 3 is a unit vector orthogonal to v and to w. Okay, let's move on to question 15. Consider the following theorem. W is a subspace of a vector space V if the following two conditions hold. The zero vector is in W. If U and V are in W and K is a scalar in the field of scalars, then U plus V is in W and K times U is in W. Now for the following W, show that W is not a subset of V and that the theorem does not hold. And I think that should say subspace, but let's see. So part A, W is the set of all triples ABC such that A is greater or equal to 0. Okay, so first notice that the zero vector 0, 0, 0 is an element of W for this one. However, for the second part of this, notice that since minus 1 is in the field of scalars, if ABC is in W, then minus 1 times ABC is minus A minus B minus C. This is not in W because minus A is not greater or equal to 0 unless A is equal to 0. So let's add the clause for A not equal to 0. A is greater or equal to 0, so minus A is less than or equal to 0. And since we've assumed A is not equal to 0, minus A is strictly less than 0. And so we see then that it's not an element of W. Okay, so the theorem does not hold here. And so this W is not a subspace of the vector space V. Okay, part B. Here W is the set of all triples ABC such that A squared plus B squared plus C squared is equal to 1. Now, is the zero vector in W? Well, no, it's not, because since 0 squared plus 0 squared plus 0 squared is equal to 0, not 1, the zero vector is not an element of W. Question 16. Let V be the vector space consisting of polynomials in one variable x, where the coefficients are real numbers and the degree n is non-negative. Let's just take some notes. Coefficients, a subscript j, are real numbers, n is non-negative, so that means n is greater or equal to 0 and n is an integer. Is W a subspace of V, where in part A, W consists of all polynomials with integer coefficients. So in part A, the a subscript j are integers. Okay, so does this W form a subspace of V? And so the answer to this is no, because K times U is not an element of W when K is not an integer. For example, if K is equal to 1/2, and then we take a polynomial U, say 3x squared plus 1, for example. So this would be 3 over 2 x squared plus 1/2, which is not in W. Okay, part B, W consists of all polynomials with degree greater or equal to 6 and the zero polynomial. So the zero polynomial is in W and the degree of U is greater or equal to 6 for all U that are in W. Okay, so using the subspace theorem above, this one here, we have 0 is in W and U plus V is in W for U and V in W. In other words, closed under addition since the degree of u plus w plus v is the maximum of the degrees of u and v. So for example, if u were a polynomial of degree 5 and v were a polynomial of degree 7, then the sum of those two polynomials would be a polynomial of degree 7, the maximum of the degree of each one, and so greater or equal to 6. Okay, so the scalar multiplication part, if k is in the field of scalars and u is in w, then we need k times u to be in w. So if we have k times a polynomial u, then this might be something like k in brackets a6 x to the 6 plus a 7x to the 7 and so on. So this is in w, because if we just multiply this through, then we have a polynomial of degree greater or equal to 6. Okay, part C, w consists of all polynomials with only even powers of x. So 0 has only even powers of x because the degree of this is 0. So the 0 vector is in w. U plus v is in w when u and v are in w, because if u has only even powers of x and v has only even powers of x, then the sum has only even powers of x. Okay, and finally ku is in w. When u has only even powers of x, a scalar multiple of that also has only even powers of x, and so it must be also in w. So the answer for this one is yes, w is a subspace of v. Question 17. Let v be the vector space of functions mapping the real numbers to the real numbers. Show that w is a subspace of v where in part A, w is a set of all functions such that f of 1 is 0. So here we have 0, the 0 vector, the 0 function is in w since 0 of x defined as 0, and so 0 of 1 is 0. So this is the 0 function. Okay, now if f1 sends 1 to 0 and f2 sends 1 to 0, then if we add these two together, f1 of 1 plus f2 of 1 has to be 0 plus 0, which is 0. Now this is f1 plus f2, the sum acting on 1, so this is 0. Okay, so now also if f of 1 is 0 and k is a scalar, a real number, then we take this line, multiply that by k, we get 0. Okay, so we have the properties required for w to be a subspace of v in part A. Okay, now part B, w is the set of all functions f such that f of 1 is equal to f of 3. So if f is the 0 function, then 0 of 1 is equal to 0 of 3. And so we see then that 0 is in w. Okay, next assume that we have f of 1 equal to f of 3 and g of 1 equal to g of 3. So then adding these two together, f of 1 plus g of 1 is equal to f of 3 plus g of 3. And so that is f plus g acting on 1 is equal to f plus g acting on 3. Okay, finally, if f of 1 is equal to f of 3 and k is a scalar, then taking this line, multiplying throughout by k, we have k times f of 1 is equal to k times f of 3. And so viewing this in a different way, k times the function f acting on 1 is equal to k times the function f acting on 3. So we have the three properties required, and so w is a subspace of v. Okay, part C, w is the set of all odd functions. So in other words, f of minus t is minus f of t. So 0 of minus t is the 0 function. This is 0, and so that's minus the zero function acting on t, and so we see that 0 is in W. Okay, next, if f of minus t is minus f of t, and g of minus t is minus g of t, then adding these two equations together, we have f of minus t plus g of minus t is equal to minus in brackets f of t plus g of t. Okay, and so f plus g as a function acting on minus t is equal to minus f plus g as a function acting on t. So the second property holds. Okay, so finally, if f of minus t is minus f of t and k is a scalar, then we can take this equation and multiply by k and express this as k of f acting on minus t equal to minus k f acting on t. And the third property holds. And so in this case, W is also a subspace of V. Question 18. Suppose U and V are elements of a vector space. Simplify 4 times 5U minus 6V plus 2 3U plus V. Now this one is incredibly easy. So let's expand. So we have 20U minus 24V. And then over here we have 6u plus 2v. Okay, collecting like terms, this is 20 plus 6u, 26u minus 22v. Okay, question 19. Looks like a fun one. Show that the axiom u plus v equal to v plus u of a vector space can be derived from other axioms. I'm just abbreviating this here. Okay, so we need to scroll up and find the axioms of a vector space, which are right here. A vector space V over scalar field K with 0 and 1 in that scalar field is a set of vectors that satisfies the following axiom. Associativity, the vector 0 is in it, which is neutral. For all u in the vector space V minus u is in V. This is the one we're trying to show. And then we have 5 through 8, which are including scalar multiplication. Okay, so where we want to begin here is starting with the expression 1 plus 1 times u plus v. Okay, so what is this? According to the fifth axiom, we can express this as 1 plus 1 times u plus 1 plus 1 times v. Okay, and then according to the sixth axiom, we can expand, hang on, we'll put by A5, and then this one we'll do by A6. The sixth axiom will tell us that this is 1 times u, or just u, plus u, and then plus v plus v. And then we have associativity, so we can express this as u plus v plus v, by the first axiom. On the other hand, if we first expand 1 plus 1 times u plus v using the sixth axiom, then we have u plus v plus u plus v. And now using associativity here, we have u plus v plus u plus v. Okay, so the two of these have to be equal. So we see then that u plus v plus v is equal to u plus v plus u plus v. And so next, what we want to do is add minus u on the left to both sides, just like this. And this is okay by axiom 3 because minus u is in v, and then the sum of two vectors that are in v is in v by axiom 5, where k is 1. So this is true by axiom 3 and axiom 5. Okay, and so next we use associativity, putting the brackets around the minus u and the u, seeing that those add up to give 0. And so what we end up with then is u plus v in brackets plus v is equal to v plus u in brackets plus v, and this occurs by associativity. Now we can do the same thing with the v here on the right hand side, adding minus v to both sides. And so when we do that, now we use the same axioms to say that that's okay. And so finally what we get is vanishing of this v on the v on the right, and so we end up with u plus v is v plus u. And so this follows from several of the other axioms of a vector space. Okay, Question 20, let V be the set of ordered pairs of real numbers. So V is the set of all pairs, A comma B, where A and B are both real numbers. Show that V is not a vector space over R, where addition and scalar multiplication are defined by, so in part A, where we have AB plus CD is defined as A plus D, B plus C, and KAB is KAKB. Okay, so let's begin with commutativity of addition. Since AB plus CD is supposed to be equal to, by one of our axioms of a vector space, CD plus AB. So this would say then that, so this one plus this one, given by this, we have on the left A plus D, B plus C. This is supposed to be equal to C plus B, A plus D. But this is not the case in general. So not so in general, since A plus D is not equal to B plus C in general. So we get a contradiction here. So V is not a vector space for the addition and scalar multiplication rules given in part A. Okay, part B, we have the rules given by A comma B plus C comma D equal to A plus C comma B plus D and K AB equal to AB. All right, so these are the rules given here. Okay, now we have A comma B minus A comma B is 0, 0, but A comma B minus A comma B is, according to this is the same as A comma B plus A comma B. And so there are two of them here. And so according to this, this is A comma B. And so this is the case only when A comma B is the zero vector.